All right. I'm in a very precarious situation, standing as the last person between you and coffee, so I'll make this quick. Good afternoon, everyone. Thank you for coming in. It's my first time at IUI, so super excited. I want to present some work that we've been doing on explainable AI around automated rationale generation. My name is Upal. Just wanted to introduce my co-authors before we start. Pradyumna, Larry, Brent, and my advisor, Mark Riddell. The work is done as a collaboration between Georgia Tech, Cornell, and University of Kentucky. And the thread that ties all of us together is we are part of the Entertainment Intelligence Lab. So let's get started. So a few years ago, I was lucky enough to test out an Uber self-driving car. So the car pulls up, and I'm expecting a backup driver, but next to that person was this operator. And the only job of the operator was to translate and think out loud on behalf of the car. And I had this pacifier tablet right here. And the only thing was to make me comfortable. Like, don't get freaked out. This is why the car is doing what it's doing. That moment highlighted an interesting challenge when it came to human-AI communication. Unlike humans, AI right now does not have that capability to express its motivation in an interpretable manner. And that makes it difficult for non-technical experts and even some technical experts to understand and trust these black box systems. And as we know, without trust, collaboration is difficult. But what if, let's say, the self-driving car, instead of the operator, could think out loud in natural language? Well, this is an aspirational goal, and hopefully one day we'll get there, depending on whether Uber's self-driving venture goes off or not. But let's get at what may be a first stab at this aspirational goal. This is what the talk is about: generating natural language explanations. In fact, generating plausible natural language explanations, because we will be considering these from a human-centered perspective in terms of how do we generate them and how do they impact user perceptions and preferences. So here's our approach. We call it rationale generation. A rationale is an explanation that justifies an action, and this is important, based on how a human would think. We're inspired by related work in philosophy of science, mind, and psychology. A special shout out to Jerry Fodor, who had this notion of the neuralese, as though we translate from a language of thought to a language of communication. So when we generate rationales, just like right now, I'm conveying my motivations and goals to you, I'm communicating in a language of communication instead of handing you out fMRI scans of my brain. So the technical intuition is that of machine translation. Can we translate sort of this kind of language that is in data structures and numbers to natural language? So instead of translating between, let's say, English and Japanese or English and Bengali, can we treat this notion of explanation generation as a translation problem? But where does these explanations come from? Well, it comes from humans doing the task and thinking out loud. We'll get over the pipeline now. So this is roughly the big picture idea, right? We're translating states and actions into explanations. This is the pipeline. I'll walk you over it. I'm going to go about how we collect data and share some tips that we learned along the way, how we use the data to train the model, and most importantly, how we evaluate this. I want to take a moment here to acknowledge that one part of the project that made it rather challenging, but also one of my favorite parts, is that in this case, generation, collection, and evaluation is tied in one pipeline, which to me was really good because it wasn't like a Wizard of Oz system and we're just evaluating the explanations. The explanations are generated. So let's look at the data collection. So collect the data, we need an environment, so we built one. I don't know how many of you are familiar with this old school arcade game of Frogger. So this little frog just has to go from here all the way to the other end, avoid some obstacles. So we built this where players can play the game and think out loud. And the design becomes clearer in the next slide. So as many of you may empathize with me, think aloud tasks are not that easy. It is challenging. And one of the challenges is to associate the action with the explanation in a tightly coupled manner. So the idea is, what if we make this into a turn-taking game? So like you take an action, you explain, you take an action, you explain. So after each action, the game pauses. We have an automated speech-to-text system that reduces the burden on the participant. So you can basically enunciate and your utterances are transcribed. And we allow the user to review and edit their explanations real time to minimize errors. Speaking of innovations and minimizing errors. The automated speech-to-text has saved us a lot of money, which is tight on a tight research budget. So we had 0 transcription costs. Thank you, Google. And then the iterative review cycles really helped us minimize errors to the point that we were able to get the data directly from the corpus and directly input into the network. Speaking of which, the network is set up as a straight-up translation problem. It's a sequence-to-sequence neural network, keeping in mind the goal is input is the state, action, and state, which is the event, the Frogger's environment, and the target is the natural language rationale. So there are 2 main configurations to keep in mind as we go through it. The first one is called complete view. In this configuration, the entire screen is taken. Random noise is injected, and the intuition is to generalize it, to make it, to force it to learn a little bit more generally. And the intuition thereby is it would produce holistic rationales. The next configuration is called focused view. In this, it's a partial window around Frogger, like right here. Okay. And no noise is injected, and the rationale is because it can't see larger than the window, it would produce localized rationales. All right, I'll give you some samples from the system. I don't expect you to read all of them, but let's highlight one of them, like complete view for an action right. I moved right to be more centered. This way I have more time to react if a car comes from either side. Just keep this in mind, like the length differences between the 2 as we go towards evaluation, because I think that will become important. All right, let's go towards evaluation. So we have gone through data collection, training the model, and then the million-dollar question is, does this thing work? And I would have been very disappointed and not be here if it didn't work. But what from whose perspective, right? Plausible from whose perspective? From a human-centered perspective. So we did 2 experiments. The first one looked at the perceptions of these 2 systems, the output of these 2 systems against baselines. And this was a within-subject study. The second one was a within-subject study. Sorry, the first one was a between-subject. The second one is a within-subject, and it looked at the preferences between the 2 outputs. So let's look at the first one, the perception study. Deployed on MTurk, 128 participants watched 5 videos of Frogger taking actions and thinking out loud. Each action is accompanied by 3 rationales. The exemplary one, which is the best human rationale for a similar or the same action. The candidate rationale is sort of like the between subject variable. So one group got exemplary candidate that was focused view. The other group got exemplary candidate that was complete view. And the bottom baseline was a random rationale, any randomly generated rationale for that action. And the goal, the bar to pass is, do you outperform random? So is there something going on in here that it outperforms random? And how far are you from the upper baseline? All right. This is just a sample screenshot from the user study. On the left-hand side, it's Frogger taking an action. We actually say what the action is in case the participant misses it. And these are some rationales. They were randomized and counterbalanced. For each action, the participants rated along 4 dimensions. And they justified their ratings using open-ended text responses. So it's not only just a quantitative measure, but I wanted to know why is strongly agree? Why does that mean? And what is the relative differences between them? These are the 4 dimensions or categories that they rated along: confidence, human likeness, adequate justification, and understandability. And we borrowed and adapted these constructs from related work in HCI, HRI, and psychology. All right, let's look at the quantitative upshot takeaway. So on this graph, the red is the candidate, which can be focused or complete view. The green is the exemplary, the best explanation, and blue is the random. So this is blue, this is red, this is blue, this is red. As you can see, for complete view, our system does pretty well against the lower baseline. For the focused view, same time. So good news for us, right? So in this round of experiments, we have established that both systems produce rationales that beat at least the lower bound. But why, right? This is where the qualitative analysis comes in. So we used a mixture of thematic analysis and grounded theory. By analyzing the open-ended responses, we clustered them along emergent themes of reasoning, and we iterated till consensus was reached about those insights. Let's look at some of the main takeaways. So for confidence, the task was around participants' faith. Does the rationale convey that did the rationale convey that the agent was able to do or complete its task? What worked really well is when there was signs of awareness and long-term planning. And what didn't work was when mischaracterizations of the environment was made or it exhibited extremely short-term planning. In terms of human likeness, if the rationale looks like it would have been made by a human being, this was very interesting because it had mixed responses and it depended on the participant's perspective on what it is to be a human. If to err is human, then slightly faulty rationales were classified as more human-like. Otherwise, if people thought computers are dumb, people are smart, then more correct rationales were classified as being human-like. That was very interesting, and it provides a really nice direction for future research as well. In terms of understandability, is how well the rationale conveys the motivation behind the action. So relatability was really important. So participants often answered, are these the same reasons I would give for this action? Things that didn't work was failure to accurately describe the surroundings, and that hindered understandability. All right, so we got through round one. We saw that we successfully benchmarked. So let's look at round two. So now what happens when you put these two types of rationales against each other? Design, very similar to the previous one. It is an online study, but in this case, instead of comparing against baselines, you are just comparing the two types of rationales. Recall that one of our intuition early on, because of our configuration, is that focused view would produce concise and localized rationales, and complete view would produce detailed and holistic rationales. One of the goals of this round was to understand how is the alignment between the intended design of the rationale types and the perceived differences. So did my intention of the way I designed these rationales actually produce perceptibly different rationales? So let's look at that. The way we sort of took at that was somewhat adventurous, which made me very nervous when we were designing the survey. We kept it pretty open-ended. We asked them, what do you think is the most important difference between the two styles? And every single participant indicated that the level of detail was important. But why? Here's a quote from one of my favorite participants. So the focused view focuses on the raw mechanics of the very next move. The complete view is broad and less focused, but takes into account the entire picture. The most important difference is the scope of events. This is powerful. This person has no clue the way we set these models up. In fact, we literally did take the entire picture for the complete view, and it is indeed the scope of events that was the determining factor between them. And it was heartwarming for me because this was a first sign of validation that the intention of the design had some alignment with the perceived differences. And I often think machine learning is like cooking. I'm not an expert, but in cooking, right, the more expert the chef is, the more accurate your predictions in terms of adding some ingredients and the output of the taste. But it's only when someone tastes your dish that they can tell you if the intended changes has had its impact or not. So this was a really good way for us to check that. Okay. We also asked people to give us a notion of preferences between the reasoning styles when it came to confidence, failure, or unexpected behavior. We asked users to imagine, like, if you had a companion robot, what style of reasoning would you appreciate when communicating these things? And long story short, the complete view configuration won in all three categories. Recall, the detail happens to be an important ingredient. So let's take a look at why. It matters because it helps develop mental models of the agent. But it plays a slightly different role depending on the context. So for failure, the qualitative analysis sort of gave us this insight that it's about proactive troubleshooting. The more detail you give me, the more things I understand to prevent future failure. When it came to unexpected behavior, though, it was about, hey, how did you do that? I don't know if you remember when AlphaGo was playing, it made some unexpected moves that was legal, but it was just super weird. And the commentators couldn't wait, what just happened? Why did it do this? So it was more like, how did the agent do it? Why did it do it? So detail plays this very interesting aspect. One thing to note, the computer doesn't need the detail, right? Like the focused view configuration with the reinforcement learner can do the job. The detail was a human factor need. So I just want to highlight that there was a really interesting way of teasing these two apart. So I've taken you through the journey, collection, training, and evaluation. Let's wrap this up. So I hope I've been able to persuade you that rationale generation is at least one plausible way to approach human-AI communication. There are many other methods that can be complementary to it, and we have a long way to get to that aspirational goal that I initially highlighted. But I hope this is a good first step. From an engineering perspective, we showed that network configurations can generate perceptibly different rationale styles. From a design side, I hope that our user study insights, and especially the data collection bit, because you can imagine, depending on, and focusing on Christine's talk as well, like the communities of practice, the explanations vary a lot depending on the communities of practice. So you could deploy a similar pipeline if you could make the tasks sort of in as much segmented manner as possible and collect similar sets of data. So I hope these kind of transferable insights can improve user engagement as you transfer these insights. I want to take the last minute to sort of highlight, right? This was, we kept the system as simple as we could. We understand Frogger is not a real world representative sample, but it was a good gamified system that showcased sequential decision making in the environment. And it gave us a really nice, simple way to get some formative understanding of the ground. Moving forward, we would like to introduce interactivity to the system. We would like to introduce contestability, like can the user contest that I don't like your explanation, try another one. And more importantly, I would personally like to look at what happens beyond the dyadic interaction of a human and a machine. What happens when there are teams of people? How does that change the role of an explanation? So those are some of the future directions we are looking at. But just wanted to thank some wonderful people, my undergrad RAs, Jiahong Sun and Cheng Han, and the amazing set of pilot testers who were patient enough with me to stick to the 10,000 iterations of the user study. I'm grateful for the funding from ONR. Would love some questions, suggestions, and feedback. And I really want to highlight that I would be more than happy to engage with you beyond just the few minutes that we have and discuss further. Thank you.
Okay, so thank you for the talk, and there's time for a few questions.
Hi, thanks. Very interesting exploration of different kind of explanations. My question is expandability. So you use a very simple example, or kind of a game, which is far more simple than realistic situations. Do you think that that actually will transform to real life? Or do you have any evidence? Because in the past, there are several different explorations with games, and in fact, it didn't scale up. So we have to reinvent everything once again, once we're moving from more complex situations.
So I would, thank you for the question. I think this is a very important factor. In terms of scalability or generalizability, my comment is the following. The game, all we need is if you can break down a task, and this is where the hard part is in terms of task analysis. If you can break down a task and you can give me an action, a state, and an explanation, I will get you an automated explanation out of that. So yes, in the game, it was easier for us to break down the sequence of actions. But in terms of cybersecurity, we are doing a field study with cybersecurity experts, and they have AI recommended threats. And when they have that, there's a sequence of steps they need to do. So all I need is a set of sequences of actions, clearly defined states, and an annotation. So the data collection process has to be replicated depending on the community of practice. Again, explanations are highly contextual, so I cannot expect them for one size to fit all unless the tasks are very similar. So yes, it's sort of like a yes or no to your question. I think it can be implemented, but there needs to be a significant amount of work that needs to be done. And what our project shows is a proof of concept of that. And you can also do that for a self-driving car in principle because there is a distinct action, a state that is recorded within the car, and you can have backup drivers to sort of think out loud as they go by. It is a resource-intensive process, but I think it is possible.
Okay. Hi, I'm Shivali from Xerox PARC. Thank you for a very interesting talk. I'm assuming that the goal of this research is to then deploy the explanation system with an actual machine learning algorithm. So then is the assumption, the primary assumption here, that the machine learning algorithm should be making decisions in a human-like fashion? So for example, like a lot of end-to-end learning systems would never even represent objects or spatial relationships like going around. And this is what the human explanations actually look like. I was trying to go around this abstraction. So like then are you making this explicit assumption that the machine learning system is now constrained to learn representations that humans reason with, and then you will be able to generate explanations?
Great question. If I understand your question correctly, I don't think so, and let me know if I'm misunderstanding it. In this case, let's say that representation, our network actually didn't learn the going around bit. It was in the language that was in the corpus when humans were doing the task. So as long as that is there, all the neural net does, especially in the sequence-to-sequence translation bit, it just learns the association between the states and actions to the explanations.
So I believe that the humans were actually trying to go around the objects. I don't think that the end-to-end learning systems would have that decision-making, right? That they are not even going around the objects. Their decisions might be based on some other statistics about the environment.
Absolutely, and I don't think that is a necessary component in this case. As long as it's in the data, as long as the actions, again, the end action, so action before, right? The state of the environment before the action, the state of the environment after the action. As long as there is a similarity between that, the system should be able to generate the closest matching rationale that was given by the participants while they were training. So if it is in the corpus, that I know what you're getting at the network level. I don't think we are task independent in this case, because the module that generates the explanation is very separated from the module that plays the game. It's a straight up reinforcement learner that just plays the game. And the module is absolutely separated from the process of playing the game. So thank you.
I think it's time to thank the speaker again.